So that's where we're going to head towards. And we're going to start by going back again to variations on the neoclassical growth model with non-renewable resources. So essentially we're going back to DHSS, but instead of assuming no technological change, no capital depreciation, we're going to bring back what we know actually happens in reality, which is that technology goes forward, capital depreciates. But to keep it simple, we make them exogenous. And then we're going to look at different resource supply scenarios, which are essentially corresponding to, in a way, these three cases. Okay, wind, coal, and oil. So, what's this one? This is wind, right? Okay, the picture is for sun, but it could have been wind. So what have we got here? The economy with a fixed flow resource. Assume balanced growth, characterized the BGP. So I'm going to pause the video here and decide exactly how I want to take you through this. Okay, so I'm going to take you through some math here. Notice it's a solo setup here, so it's simplified, it's not Ramsey. We've got a fixed saving rate, S. Okay, so this is very, very simple model. Okay. And I got a bit lazy when I was drawing this, so we haven't got that. I'm not showing the capital stock, but of course that investment is feeding into the capital stock, and then capital K is the input, right? It's not SY that's the input, it's capital K. So what have we got? I'm going to go over to here, and we have Y is ALL 1 minus alpha minus beta, K to the alpha, R to the beta, and AL is growing at a rate G, and then we have a capital accumulation function, K dot, the rate of change, or the change in capital, is the additions to capital minus the loss of capital. Okay, so assume balanced growth, characterize the BGP, balanced growth path. So why would we assume balanced growth, and what is balanced growth? You should all know this. Okay, if you've done macro 1, you should all know what balanced growth is. But balanced growth, or a balanced growth path, is a path on which the state in general, the state variables all grow at constant rates. Okay, things change at constant rates on balanced growth. And a rate of change we denote by it. So this K dot, that's not a rate of change. Okay, K dot is addition of new capital. That's sort of like a physical addition. But the rate of change of capital in like percent per year, so to speak, loosely, is K dot over K. It's new capital in relation to the existing stock. Okay, that's the rate of change. So for balanced growth, K dot over K should be constant. But K dot over K, of course, is SY over K minus delta. Okay, we'll go back. Whoops. Sorry. We'll go back to the math shortly, but why do we look at balanced growth at all? Well, it's fundamentally this idea from the looking at the Solo model that actually we can start with the capital slightly out of kilter, slightly too much or slightly too little, or even a lot too little, but within about 20 years we're going to be pretty much on the balanced growth path, right? Because if you've got too little capital, you invest in more capital, but the depreciation is lower because there's not many machines to depreciate. You rapidly build up the capital stock. and both the theoretical models parameterized to fit how we see real economies working, it shows that these processes don't take that long. So economies where everything's been, or huge amounts of capital have been destroyed for different reasons, we see that they rapidly recover. So it's just not that interesting to look away from the balanced growth path. And of course, it's a lot easier to look at the balanced growth path. So we're just going to go straight there. So what does the balanced growth path look like? On a balanced growth path, we know that k dot over k must be constant. Okay, it's not necessarily zero, but it must be a constant. Delta is constant, so that means that y over k must be constant. If a ratio of two things is constant, that must mean that they're growing at equal rates, right? So that means that y dot over y equals k dot over k. If y is growing at 3% a year, k must also be growing at 3% a year, okay? So in general, growth rates must be constant on a balanced growth path. Here we see that in this model for balanced growth, we require that y and k not just have constant growth rates, those growth rates must be equal. Okay. What's the other thing we need to do? We need to differentiate y with respect to time. And when we differentiate y with respect to time, we differentiate it with respect to each of the variables, and then we differentiate the variable with respect to time. And then we add up all the effects, right? So if AL is increasing, how much does y increase? Well, dy dt is dy dAl times dAl dt plus dy dl times dl dt plus dy dk, dk dt, etc. Okay, we're going to assume no population growth here. So we can drop dy dl. So we've got y dot dy dt is dy dAl. What's dy dAl? Al to the power of this. So it's 1 minus alpha minus beta times everything divided by Al, because we're dropping a power of 1 on Al. So the whole thing is just y, so it's 1 minus alpha minus beta times y over Al. And same method here, it's alpha times y over k plus, oh, who spotted my deliberate mistake? 1 minus alpha minus beta times y over al, but then we need to go dal dt, right? So then it's al dot alpha y over k, k dot, beta y over r dot. And if we divide through by y, we get y dot over y, 1 minus alpha minus beta, al dot over al, plus alpha k dot over k, plus beta r dot over r. Okay. So far so good. The growth in y depends on the growth in these three variables multiplied by their sort of weights in the Cobb-Douglas function. It makes total sense, right? But now we use this and we can say that, oh, this is just y dot over y. So if we take that over, we have 1 minus alpha y dot over y is 1 minus alpha minus beta, and this we defined as g plus beta r dot over r. So if we divide by 1 minus alpha, we end up with, oops, that's the notes from earlier. just about see this. We'll go on to the separate page, sorry. We end up with y dot over y is 1 minus beta over 1 minus alpha g plus beta over 1 minus alpha r dot over r. Okay. Is that enough? I'm just going to pause there and collect my thoughts here. Yeah, I think this is basically where I wanted to get to here. But so G, these are all parameters, but R dot over R, we don't really know. If we knew more about utility and so on, we could find out what it's going to be, but I'm not sure I want to go into that right now. It's not that hard actually. But if we think about when we talked about the DHSS, we've got this restriction that the total resource use can't exceed the stock, right? Yeah, sorry, of course, how stupid. We're in the case with sunshine. So what's R dot over R? It's 0, yeah, because R is the flow of sunshine, it's just constant. Sorry. So in this case, we can just wipe that, and y dot over y is this. So it's G minus this. So if beta was 0, then we wouldn't need the resource input, then y dot over y would be G. So this minus term here is a sort of penalty for how much the need for this resource input that cannot grow, how much that sort of breaks the growth process overall. Okay, the representative final good producer must hire labor, capital, and land, or sunshine, whatever. Okay, we're assuming there's a perfect market for sunshine. It could be you need land to harvest the sunshine, for instance. But apparently you don't need any inputs to do that in the way we've set this up. But there's a perfect market. Okay, so what will the price be? Well, let's do it properly. So we want to set up the profit maximization problem of a representative final good producer, where the profits is PYY, where y is given by this. Okay, I just want to save ink by not writing that out. PY is the price of y times the quantity minus the input costs. So that could be, like, we could call it WLL minus WKK. We don't usually use WK for the price of hiring capital, but I'm going to do it. Minus WR. Those are the input costs, right? What was the question? What happens to the price of land over time? Okay, so R is land, or the price of this flow of resources. And WR is that price. Okay, so what happens to that over time? Well, to find out more about this price, we take first order conditions, right? It's like, how badly does this representative producer making profits pi, how badly do they want the land, or this flow of inputs R? So we go d pi by dr is, and by the way, py we just normalize to 1, right? Py, that's the price of, like, hammers or whatever, and we normalize that to 1, so we can skip that. d pi by dr is dy by dr, so if we go back here, it's beta times y over r. No r's here, minus wr, so if we put a colon here, we can save some ink and write like that. Beta y over r equals wr. So Y we know is growing like this, so clearly WR, R is constant, so WR will grow at the overall growth rate. So the price of land will grow at the growth rate, the quantity stays the same. Okay? So that we've characterized the model. Okay. And if we'd actually looked at land markets and things, this actually makes a lot of sense, right? Okay.